Hope you are doing good. Since we keep on meeting each other in the doubt clearing sessions and discussion platform, hope you haven't forgotten solid state till close packed structures and the numericals related with unit cell and close packed structures. Good. Today, let's move on to the next topic in solid state, that is packing efficiency or packing fraction. Efficiency. It is not a new term for you. If a teacher teaches a difficult concept very clearly in a short or a limited time period, that too in a single explanation, we name that teaching as effective or efficient teaching. If a fuel makes a vehicle go or move for a long distance by using a limited amount of fuel, we name that fuel as efficient fuel. Similarly, if a large number of substances or particles can be accommodated in a limited space, we name that packing or arrangement an efficient packing. In the previous sessions, we have seen different types of packing or arrangement or close packed structures. They were simple cubic close packed structure, then cubic close packed structure or hexagonal close packed structure, and one more is there, body centered cubic close packed structure, where body centered unit cells are arranged in a regular fashion. Now let's define what is packing efficiency. It is said packing efficiency is the percentage of total space occupied by particles in a crystal lattice. Once again, let me repeat. Packing efficiency is the percentage of total space occupied by particles in the crystal lattice. Is this concept clear to you? Or suppose I have a box and I want to fill it with mini balls or small balls. I completely fill the box with the balls, and I found that only 3/4 of the space is occupied and 1/4 of the space is left as voids or interstitial sites. Here, the packing efficiency is 3/4 into 100, which is equal to 75%, and the empty space percentage is 25. It is said packing efficiency of hexagonal close packed or cubic close packed structure is 74%. Packing efficiency of body centered cubic packing is 68%, and packing efficiency of simple cubic crystal lattice is 52.4%. Now, we will see what is the formula or how to define or how to represent packing efficiency. Packing efficiency, I told you, it is the percentage of total space occupied by the particles, or it is given in the form of a formula as PE packing efficiency. It is volume occupied by particles in the unit cell divided by total volume of the unit cell into 100. We know volume occupied by particles in the unit cell mean number of particles into volume of one particle, and we know all the substances, these particles, actually it mean atoms. So packing efficiency is equal to number of atoms into volume of one atom divided by total volume of the unit cell into 100. It is written here, packing efficiency is equal to volume occupied by particles in unit cell into 100 divided by total volume of unit cell. Or it is equal to number of atoms. I told you particle mean atoms. Number of atoms into volume of one atom into 100 in order to convert it into percentage divided by total volume of unit cell. Now we will see the packing efficiency of each closed pack structure. To begin with, XCP or CCP structure. XCP, hexagonal closed packing. CCP, cubic closed packing. We know what is XCP, where the particles are arranged in the pattern A, B type. And CCP mean the arrangement is following the pattern ABC pattern. And X-ray diffraction studies have proved that the packing efficiency of XCP and CCP structures are one and the same. They are equally efficient and its value is 74%. Now we will calculate how we are getting this packing efficiency of these structures as 74%. For that, we will take the unit cell of a closed packed structure, which is face-centered unit cell. It is shown here, a face-centered unit cell. Only one face is arranged with atoms in order to avoid mess. So this is a face-centered unit cell, and at the face-centered unit cell, its features. Particles are present at all the 8 corners, plus particles are present at the center of each face. One face is shown. And we know, please children, please do remember the expression for packing efficiency, which is number of atoms into volume of one atom divided by total volume of the unit cell into 100. For FCC or face-centered unit cell, number of atoms is 1 by 8 into 8 plus 1 by 2 into 6, which is 4 atoms. So number of atoms is 4 into volume of one atom. We know atom, it is spherical in shape. It is considered as spherical in shape. So volume of one atom is 4 by 3 pi r cube divided by total volume of the unit cell. Unit cell, it is in cubical form or it is having the shape of a cube. So here it says, let the edge length be A. Let the edge length be A. So using that edge length, now we know what is the volume of the unit cell. It is A cube. So we got an expression for packing efficiency, which is 4 into 4 by 3 pi r cube divided by A cube into 100. And here it is written, radius of the atom be r. That's why we have taken its volume as 4 by 3 pi r cube. Now, the phase diagonal they have given me. Why we need these parameters? We have seen the expression for packing efficiency is 4 into 4 by 3 pi r cube divided by A cube into 100. Here we are not getting a constant value as 74%. So here the problem is we need to convert A in terms of R. Then only we can cancel the common terms and we will arrive at a constant value. For that only they have taken the phase diagonal AC as B. See what is AC? Here in this diagram, we know we are considering this is the phase diagonal where through which atoms are marked. Here the corners of this unit cell, it is marked here A, B, C, D, E, F, G, H. and this distance AC is marked as B, and we know what is DC, it is edge length only A, and what is AD, this is also edge length, which is A. So applying Python, now we will see here, face diagonal AC is B, as per the definition, packing efficiency is equal to number of atoms in the volume of an atom divided by volume of unit cell into 100. Again, till this expression I mentioned before. Now from the triangle ACD, now which is the triangle ACD, this triangle, right angle triangle. So in order to find the distance B, we can apply Pythagoras theorem. So from the triangle ACD, on applying Pythagoras theorem, we get AC square is equal to AD square plus DC square. Again, AC square we know it is B square. AD and DC, they are edge length, so that's why it is written here B square. B square is equal to A square plus A square, which is equal to 2A square, or B is equal to A root 2. B is equal to A root 2. Why we are doing all these things? I told we need an expression of A in terms of R. So again, so we got this is the first equation for B. B is equal to A root 2. Again, we know this B, it consists here in the solid triangle 3, and in this solid circles or atoms, 3 atoms are given. We know in terms of radius. What is this B? B means this half radius, this is radius, this 2 radius, that means this is full diameter, this is also radius. So how many radius comes here in this B, the face diagonal? 2R plus R3R plus R4R. So we got 2 expressions for B. One is B is equal to A root 2. The second expression, again from the diagram, we know B is equal to 4R. Now equate these two equations. B is equal to A root 2, B equal to 4R. So A root 2 is equal to 4R, or A is equal to 4R by root 2, or A is equal to 2 root 2R. Now we got an expression for A in terms of R. Now we will substitute it here. Substituting A in packing efficiency expression. Packing efficiency for CCP or XCP structure is 4 into 4 pi r cube into 100. 4 pi r cube, 4 by 3 pi r cube into 100 into 2 root 2r. What is 2 root 2r? It is A. So 2 root 2r the whole cube. So we are getting a chance to cancel this r cube and r cube, and we will reach at an expression C. 4 into 4 by 3 pi r cube into 100 divided by 2 root 2r the whole cube. 2 cube, 8. Root 2 cube is 2 root 2 into r cube. So now we can cancel r cube so that we will reach at a constant value, and it is none other than P is equal to pi into 100 by 3 into root 2. Root 2, its value is 1.414, and we reached at 74%. So the packing efficiency of hexagonal closed packed or cubic closed packed structure is 74%. Dear students, for the examination I have seen questions being asked as, what is the relation between edge length and radius in a CCP structure? Edge length and radius. Here we know edge length and radius. We have seen edge length A is equal to 4r by root 2, or A is equal to 2 root 2r. Please don't forget these equations. We need to, questions are there. Sometimes questions comes as derive an expression for packing efficiency of CCP or XCP structure, or as a 1 mark question they are asking as what is the relation between edge length and radius of an atom in the CCP crystal lattice. Hope it is clear to you. Now move on to the next packing efficiency of BCC structure, body centered cubic structure. And I told you before that its packing efficiency is 68%, and we will see how to reach that packing efficiency in BCC structures. Here a body-centered unit cell is shown. Body-centered unit cell. Hope you remember. How is it? Body-centered unit cell contains an atom in the center, body center, which it is not, that atom is not sharing with any other atom. Plus, at all the 8 corners atoms are present, but its contribution to a particular unit cell is 1 by 8. So, for a body-centered unit cell, number of atoms is 1 by 8 into 8 plus 1, which is equal to 2. Next, packing efficiency, we know number of atoms into volume of one atom divided by total volume of unit cell, which is equal to A cube into 100. Here it is given, let the edge length be A. Edge length. Edge length is only these distances like ED or DC or AD. These are edge lengths. Now, and here also it is given, radius of the atom is R. Radius of the atom R. In the previous for CCP also we have seen this. Now here we have to consider 2 diagonals. Face diagonal, which is given as small letter B, and body diagonal, which is given as C. Because body diagonal, why we are considering? In body-centered unit cell, one atom is present at the body center. So we have to consider that distance, which is represented by C. C, it is given AFC, and we have to consider diagonal distance. That means we are considering this distance which is inside the board and this A which is on the plane of the board. So this distance is body diagonal, which is represented as C, and this distance by one face FD, it is considered as B. Now in what we are going to do, we need an expression of A in terms of R. That is why we need to consider this triangle AFD. But FD is B, AF is C, and AD is A. We know only the edge length A. So first we need an expression, or we need to find an expression for B in terms of A. Then we will need an expression for C in terms of A. So first we will find what is B, then we will see what is C. Anyway, in order to find B, we will consider the triangle EFD. Then for B, which is the hypotenuse, ED, it is one side, EF the other side, which is, so we can say the value of B right now. B square is equal to A square plus A square, or B square is equal to 2A square. That B value we have to apply here to find the length of C. That is what we are going to do here. Let's see. Let the edge length be A, radius of the atom R, face diagonal B, body diagonal C, and packing efficiency is equal to 2. Number of atoms in body-centered unit cell. 4 by 3 pi r cube divided by A cube into 100 is there in triangle EFD. EFD means about on the face it lies. We found B square is equal to A square plus A square is equal to 2A square. I know you are well versed in this because we did the same pattern for finding the packing efficiency of XCP or CCP structure. So we found B is equal to A root 2. Now we are considering the other triangle which passes through the body diagonal. Again, C square is equal to A square plus B square. You have any doubt? Look, C square is equal to A square plus B square. C square is equal to A square plus B square. The same thing we are applying here. C square is shown is equal to A square plus B square. But B square we know. B square is 2A square. So we are getting C square is equal to A square plus 2A square, which is equal to 3A square, or C is equal to root 3. Root 3A. C is equal to A root 3. That is first equation. Another equation is body diagonal. Body diagonal means in the center one atom, at the corner half atom, the other corner half atom. Or we can say C is also equal to 4R. On equating these two, we will get A root 3 is equal to 4R, or A is equal to 4R by root 3. So we got an expression of A in terms of R for body-centered cubic closed packed structure. So packing efficiency is equal to 2 into 4 by 3 pi r cube into 100 divided by 4R by root 3 the whole cube. We can cancel R cube because this is 4R by root 3 the whole cube. So we can cancel here R cube, R cube. So we can reach at a constant value. And on substituting these values, pi 3.14, root 3 1.732 into 100 by 8, and we will get a constant value of 68%. So this derivation of the packing efficiency of body-centered cubic structure is also important, and we found that it is 68% and the empty space percentage is 32%. Here also you have to remember one thing, the relation between edge length and radius of the atom. Edge length is A, radius of the atom is R. A in BCC is equal to 4R by root 3. Dear children, now we will move on to finding the packing efficiency of simple cubic crystal lattice, which is made up of cubic unit cells. It is very easy. No need of explaining even it seems. We know for a simple cubic unit cell, particles are present or atoms are present only at the 8 corners. And no atoms are present in between the face or in the body center. So here itself it is shown. This is the way of arranging the simple cubic unit cell. And here this distance edge length A and radius R and 2R constitutes one edge length as no other atoms comes in between. So easily we can say let the edge length be A and the radius is R, and we know the relation between edge length and radius. It is A is equal to 2R. Now apply the expression for packing efficiency, which is equal to number of atoms in simple cubic unit cell. Number of atom only 1 by 8 into 8, which is 1. 1 into volume of the atom, which is spherical in shape, 4 by 3 pi r cube into 100 by a cube. We know A is equal to 2R, so 2R cube. On substituting, we will get pi by 6 into 100, which is none other than 52.4%. So my children, from the examination point of view, the questions that can come are 1. Derive an expression for the packing efficiency of XII CCP structure or BCC structure or simple cubic crystal lattice, or the relation between edge length and radius in these 3 structures. Now, hope this thing is clear to you. Now move on to the next topic. Density of unit cell. How to find the density of unit cell? In numericals, mostly this question comes. Find the density, or they will give density, they will ask you to find any other parameters. So, density. From class 6 onwards, we are studying the expression for density, which is equal to mass by volume, or in this case, we will say mass of unit cell by volume of unit cell. Volume of unit cell, we know unit cell is having the shape of a cube. So volume of unit cell is a cube, and then mass of the unit cell. Mass of the unit cell. If it is FCC, we know 4 atoms are there, and the mass of the unit cell can be written as number of atoms into mass of 1 atom. Usually in the numericals they are giving, it is represented here, density is represented as D. D is equal to mass of the unit cell by volume of the unit cell, or number of atoms into mass of 1 atom. divided by volume of the unit cell. Let the density be small letter d. Let the edge length is a. Number of atoms here in the textbook also it is given as z or we pronounce it as z. And molar mass will be given. Sometimes they will give NaCl. Then we can find the molar mass or they will give the molar mass. Let the molar mass be M. Avogadro number be Na. Why they have given Avogadro number? Or we know Avogadro number from class 9 onwards. We know its value. 6.023 into 10 raised to 23. Molar mass means mass of Avogadro number of atoms. If we know molar mass, if we know the Avogadro number, we can find the mass of one atom which is equal to molar mass divided by Avogadro number, that is mass of one atom. So density, mass of one atom becomes M by Na, or density becomes number of atoms Z. If it is FCC, it is 4. If it is BCC, it will be 2. If it is a simple cubic unit cell, it will be 1. Is that value? It changes depending on the various close packed structures. A cube. M by Na is mass of one atom. A cube, it comes in the denominator because it is the volume of the unit cell, and we get the expression for density as Zm by A cube Na. So please children, don't forget, I told you for the numericals these questions come. Sometimes they will ask you, find the value of edge length. They will give density. They will say which type of crystal is that. Molar mass they will give. Avogadro number we know. So that is about the density. Dear students, the numericals related with this topic is already uploaded in your Teams files. Please download it and try to solve. If any doubt, it will be clarified in your discussion platforms. Dear students, please develop a nature or habit of going beyond syllabus. When I went through the question papers of different competitive examinations, I found that there are questions related with radius ratio, which is a topic which is much closer to this, which comes in the solid state, coordination number and geometry of the crystal and its interdependence too. If we meet each other in the class, we will discuss these things. Dear children, let me wind up. Hope you understood the topics being taught today and hope you will study well. In the next session, we will discuss on imperfections seen in crystals. Till then, take care. Thank you. Bye.